Cool. Hey everyone, welcome. My name is Ashwin, and I'm joined by my friend and co-host ZY, who also has a PhD in machine learning. Um, Besides being an engineer, I'm also an artist. I do a lot of visual art, particularly drawings. And this is the Creative AI podcast. So, we're really interested in the intersection of art and AI, and we're here to explore exciting developments in this area and share everything with you. All right, let's dive in. So, in this first episode, we're just going to keep this as a simple Q&A format. I'm going to be asking some basic questions to ZY, and then, let's dive in. Hey, ZY, welcome.
Hey, Ashwin.
Alrighty, let's jump in. So, ZY, there's been a lot of buzz around machine learning, deep learning models for creative use cases in particularly visual art. It all started with OpenAI's DALL-E, and then Stable Diffusion made it open source, and then there's it's become like super popular. So, could you help us understand what is the technology trajectory that happened, let's say in the past 5 years or 10 years, that got us to this moment? What were some previous models? What were some limitation? What was that secret sauce that helped, come to this moment?
Yeah, this is a very big question. And I think mainly there are three critical advancements that brought us here. First is the rise of neural networks. I say it's the rise of neural networks because neural networks has been here for many years, many decades, probably in the 80s. But people didn't realize how powerful this model is. And recently there are a lot of new inventions of the so-called backbone models. For example, in language, we invented the transformer model in 2017. And in the vision, we have a lot more models like different variations of convolutional neural nets, such as UNet, ResNet, etc. And what's so powerful about such neural networks is that they are capable of modeling any kind of tasks as long as their input are language or vision. And in the past, language and vision are very difficult to deal with. You have to do a lot of handcrafted feature engineering to make them suitable for modeling. But with neural networks, with those big backbone models like transformer and vision, now we don't have to worry too much about how we deal with those input. We just feed them into a network, and it gives you some output, and you use it to do whatever task you want. And I think the second thing is the huge amount of data.
Mm-hmm.
And all those kind of careful processing of those big data by big companies. And it actually has two outcomes. One is that our model becomes more powerful in particular task. And it also empowers us to pre-train some models, some backbone models that are suitable for fine-tuning on particular tasks. So your backbone model is pre-trained on a big amount of data, and it has some general knowledge of something, but it probably doesn't do any concrete tasks. But when you further fine-tune this model on some particular data, it is capable of doing something very fancy, such as text generation and things like that, and image generation. And I think the third thing is the infrastructure we have to support all those kind of massive model training with huge amounts of data. This is not really feasible to do it with your personal computer. It's only doable with distributed training by big companies, big tech giants. And also the advancement of chips. We now have GPUs to train the big models. So these are, I think, these three components. The first is the invention of new neural network models and realizing how powerful it is. And second is the big amount of data we collect from the open web. And third is the infrastructure we use to train those big models and use them to fine-tune on a relatively smaller data set to build particular applications. I think these are the three critical components that brought us here. And you also asked about what were some previous models, what were the limitations and things like that. And I think previously, I think about 15 or 20 years ago, people were thinking that vision problems we won't be able to solve them in our lifetime. We won't see us predicting, classifying images and things like that in a short period of time. But now, when we look back, image classification seems to be an easy task. We can do much more than just classifying images. We can even generate images. We can edit images. We can generate very natural descriptions of the images. And those are all mainly, I think, caused by neural networks and big data. But back then, we do a lot of hand-tuned feature engineering. I think people spend a lot of time on linear algebra. I was not in that era, so I don't know too much about what people were doing back then. But definitely there are a lot of feature engineering, like for languages like n-gram extraction, and then you do classification based on SVM or things like that. Those were feels like a long time ago.
Great.
I think those were my answers.
Yeah, I think. Thank you for explaining that. I think it's important for especially young people and someone new to this field to understand. There's a lot of engineering work and evolution, both in algorithms and computation models, plus the confluence of hardware such as GPUs. That's kind of like triggering this revolution. But again, the point is, there's a lot of heavy computer science work that's happening behind the scene.
Right.
It might look very fancy and simple in the front end, but I think it's to the audience watching. I think it's very important to kind of dig into what those evolution of models were, if you really want to get into actually developing or extending any of these capabilities. All right, that's awesome. So let's jump in and kind of go a little bit deeper. Maybe some of the popular tools are DALL-E and let's say Stable Diffusion. So if you were to unpack the capabilities of these platforms or tools, let's say, I'm describing a concept in natural language, draw me a picture of Silicon Valley and Van Gogh style, and it generates an image. So maybe in like 2 to 3 minutes, could you explain what happens in the backend when a simple natural language text is fed into the model and to generate an image?
Okay, so I think at the very high level, I would describe it as an architecture of an encoder-decoder framework. It probably it's more like more than a framework. It's a mindset in any kind of creative art generation. We are always encoding something from language or image to a latent space. By latent, I mean it's not something you can observe. It's like in your mind, you have a concept. And there's also a decoder model that decodes from this latent space to something that you can perceive, like an image or some audio or text. And so this encoder-decoder framework was first invented for machine translation. The idea is that, let's say if you want to translate Chinese to English, we believe that although they are two different languages, but all the concepts and all those concepts and the ideas are the same in a latent space that you can't observe. Whenever when you speak English or Chinese, you're probably thinking about the same thing. So the model tries to figure out, can I first map a language into something that is lower dimensional? By lower dimensional, I mean text feels like it's infinite dimensional. And when you map it to a lower dimensional space, you're encoded into some vectors, and then you decode it into some other language. And the same mindset can be applied to any kind of translation tasks. For example, in image captioning, you have an image, and I first encode it into something in the latent space and decode it into text. And in generation, you first input the text. The text could be encoded by a transformer network. Remember, I said transformer is a commonly used backbone model for text. Whatever text you have, you can encode it with transformer. And then you have some vectors in the latent space. Then using those latent space vectors, you can figure out how to guide the generation process to generate a beautiful image with the concept of the text. And I used to have a professor who likes to think about all those machine learning problems as information theory compression problems. It's all like you have you have the raw data, and then can you build a model to compress them to as few bits as possible? Because if you can compress them, you kind of learned some high-level concept of the object you're trying to encode. And the decoder model, there are many common models to do that. In text, it's usually a transformer decoder. In vision, it's usually ResNet. I think UNet is a model that people commonly use to generate images. So the encoder-decoder framework, I think, is the core concept of image generation.
Awesome. Yeah, I think that's a really good framework to to keep in mind, is to look at all this from an information theory. I would definitely encourage all the audience to look at Shannon's work in information theory. I think a lot of our modern day technology kind of we're really thankful for what Shannon did. I don't know, back in 40, 50 years back.
Yeah, and I think what's unique about machine learning is that you don't know what's the encoding process. You're just giving. You design some framework to do the encoding and decoding process, but the real process is learned via data.
That's
and
true.
You just want to compress the data in some way.
Awesome. Let's jump into a little bit of more, I would say, like a tactical question. So, is there, you talked about the general idea of looking at text to image generation from machine learning information theory. Is there anything unique, particularly about OpenAI's DALL-E or Stable Diffusion, either in terms of their computational brilliance, or is there anything distinct about other capabilities, such as, hey, they have pretty much a lot of money to buy compute infra, that's why they're able to do it. I'm just curious, like, is there something that stands out to you, either theoretically or practically, why these were successful?
Yeah, I think the huge amount of data and their huge parameter sets I would say they are the most critical components, because I'm not fully convinced that we have yet discovered the best model yet. I believe that in the near future, probably new models will come out and people will say, we now have a better model than Stable Diffusion and DALL-E. But that being said, their models are still pretty good. So if I remember correctly, DALL-E 1 and DALL-E 2 are actually quite different in terms of their modeling techniques. DALL-E 2 also uses diffusion models, but DALL-E, I think, does not. And Stable Diffusion, of course, is a diffusion model. So what's unique about these models are that sorry, can we recall? I think I forgot what I want to say here.
It's okay. Take it on.
Can you edit your video later?
Yeah. I can edit.
Yeah, that's fine. Then maybe we start from this part. You ask again the question, and I
Sure.
answer again.
Okay, so yeah, let's move on to the next one. So you talked about, in general, how a typical text to image generation works in terms of, encoder, decoder. But right now, DALL-E 2 and then Stable Diffusion are the most popular models. Is there something that stands out to you, either from a computation algorithm perspective or more from a practical, infrastructure perspective that you want to highlight? Like, what makes these special? Were they just lucky? Were they the first to come out, or is there something distinct that stands out in these two models?
I think the success of DALL-E 2 and Stable Diffusion are a demonstration of perfect combinations of both theoretical work, modeling, engineering, and everything. It's all teamwork. That it's very hard for someone alone to achieve this big success. So definitely they have huge amount of data. I don't know where they collect all of this data. I think probably from Open Web, and the huge parameter sets that also helps a lot. In terms of modeling, they use diffusion models. But if I remember correctly, DALL-E 1 and DALL-E 2, they are quite different in terms of their modeling techniques. DALL-E 2 uses diffusion models, DALL-E 1 probably does not. But actually, I believe that we probably have not yet discovered the perfect modeling for image generation. Maybe in a few years or a few months, we'll see people coming up with new models saying that they work even better than Stable Diffusion. That's totally possible. So I think one thing for sure that we are very clear about is that huge amount of data, bigger modeling size usually helps.
Awesome.
And as I said, these models are also perfect demonstration of the encoder-decoder framework, where you encode text into something in the latent space, and then you guide the generation of images with that textual input in the latent space to slightly modify the image.
Got it. That's super helpful. Let's go into our final question. So, I've seen the word diffusion kind of been fancy all over the internet. Could you help us understand or unpack what is a diffusion model from a computer science perspective, and how does it kind of relate to, let's say, generating art from either text or, maybe like you input an image and it generates like, different styles of an image, for example. So what is the diffusion? How does it connect with kind of creative use cases?
Yeah, so I think it all comes back to when we think about the generation of image, we can do it in different ways. I think previously people were thinking about we can, for a convolutional neural network to classify an image, you want to encode the image more and more to make it in a smaller, lower dimensional space, and then you can do classification or something else. But if you want to do generation, it's like a reverse process. You have a latent vector, and then you want to slowly deconvolute it into bigger sizes. But I think DALL-E 1 uses that kind of technique. But later on, people find there are better ways to do image generation. Better in the sense that they are state of the art as of today. And diffusion models, there are a lot of noise around me. I think we probably need to do it again. Can you hear the?
I can hear you. Okay. Do you want to?
Okay.
Yeah, I can. Yeah.
Let me start again. Can you ask the question again? What is diffusion model?
Yeah. So let's go into our final question. So there's been a lot of buzz, particularly around the word diffusion, primarily due to the Stable Diffusion tool. But from a computer science perspective, could you explain what a diffusion model is, and why is it so kind of core or central to kind of creative use cases such as text to image or image to image generation?
Right. So I think before we talk about diffusion models, we need to first understand how the process of image generation works. So if we think about image generation is essentially a reverse of image classification or something like image encoding. Let's say if we want to classify an image into different categories, what we do is we usually apply a convolutional neural network iteratively to reduce the dimension of the image to something in a lower dimensional space, in a latent space, and then you can do classification or whatever. And the image generation is a reverse process. You start with something in the latent space, in a low dimensional space, and then you deconvolute it into something of bigger size, and then you do image generation. And I think that's how DALL-E 1 does it. And diffusion model is quite different. And it seems to be working a lot better as of today because they are state-of-the-art as of today. It comes from physics or thermodynamics. If you observe how elements move in physics, they kind of follow a Brownian process to Brownian movement. If you drop an ink into water, the ink elements will spread all over to the water. So an analogy here in the image generation process is like we can think about if there is a perfect image, you already have an image that, let's say it's a cat or a dog or something recognizable. We can slowly inject noise into every pixel. And after a few iterations, let's say 100 iterations, the image will be totally not recognizable. It becomes pure noise. And the diffusion model tries to do the backward. They want to start with some pure Gaussian noise, and then you slightly denoise the model iteratively, and finally, by denoising, I mean you manipulate every pixel. And how do you manipulate it? You build a neural network to predict how you can manipulate it. And then eventually you recover the process and you have a recognizable image that is very high resolution, very beautiful. And this is a very flexible framework because you can also add text features into the reverse process. You can build a model based on the current very noisy image pixels, and you can add the text feature, and your model take both features and recognize and realize how you can adjust the image a little bit to make it more recognizable. And after many iterations, you're recovering a beautiful image from a very noisy Gaussian noise picture. And Stable Diffusion has some special tricks to make it work even better. They do the denoising process in a latent space rather than in the real pixel space. And I believe people can still do a lot of things to figure out where you can do the denoise thing. You can do it in the latent space or in the real image space, and then finally you have something beautiful.
So I understand what a latent space is, but for someone who's not from a computer science concept, what does a latent space mean? Like, is it the potential space of all possibilities, or what do we mean by latent space for someone who's not completely into computer science?
I think a latent space is something that is not observable. If we think about images, they are essentially our observation of the world with visual color. In terms of computers, it will be raw pixels. Let's say if you have a 200 times 200 pixel images, and each pixel will come up with 3 values representing their RGB values: red, green, blue. And I think these are the 3 pixel values. And these are the raw input, but they are too high dimensional. Let's say for 200 times 200 times 3, it's a very big dimensional space. And in reality, we actually don't have that many core concepts to remember when we perceive the world. Our brain is doing something to map our world to some neurons in our brain. and it's probably lower dimensional. You just need need lower dimensional vectors to remember everything. And here the model is trying to do the same as our brains do. We process the raw input to something of a lower dimensional space, and you have a vector to recognize the whole world, to perceive and understand the world. So I would say latent vectors are concepts in our brain. Each vector probably represents some vector. There were, I think in DALL-E 1, they even did something to map everything into a discrete space. So the latent space can be discrete or continuous. If it's continuous, it feels like you still have an infinite number of possibilities. If it's discrete, you have much less choices to map those concepts.
Yeah, I think that was a really good explanation. So I think for this episode, we're done. So in the next episode, we'll try to uncover a little bit more of the technical foundations of creative AI. And thanks everyone for listening. And thanks
Thank you
for taking time to explain all this.
Yeah, thank you, Ashwin.
Cool. Just hold on. So I'm going to